Today we're going to look at the Lagrange Error Bound, which is this complicated looking formula that most students learn at the end of a Calculus 2 or BC Calculus class. We're going to get a full understanding of where this formula comes from by looking at its derivation. So to start, let's look back at Taylor series, what they are and what they were used for. So a Taylor series is used to write some continuous differentiable function, f of x, as an infinite sum of polynomials, which is written as f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared all over 2 factorial, and this pattern continues forever. Now, the reason we use Taylor series is to approximate the value of f of x. However, in the real world, we're not going to sum up infinite values to approximate f of x. What is normally done is they take the first n terms and use that as an approximation. Now the question becomes, how good of an approximation is it? Of course, as n tends to infinity, the approximation gets better. But for an n-term polynomial, how good of an approximation is it for f of x? Or in other words, what is the error in this approximation? So we can write our error as some function, let's call it r sub n of t. We're going to use t because we'll use x later. And this is just going to be the difference between the actual value, which is f of t, and the approximate value, which is going to be what we get from our Taylor polynomial. So we'll call that p sub n of t for the n-term polynomial. And our end goal is going to be to find some value, or some bound in this case, for the error. Now to start, we can just evaluate the entire right-hand side by looking at the Taylor series, because f of t is just the infinite series, and p sub n of t is just the first n terms. So their difference, f of t minus p sub n of t, is just going to be the rest of the terms. So the n plus 1 term, the n plus 2 term, and so on. So what that's going to be is the n plus 1 derivative at a times x minus a to the n plus 1 over n plus 1 factorial, and so on. Well, actually, this x should be a t, because we're writing this as functions of t. So now we have an exact formula for r of t. However, we don't want an infinite formula, we want a compact, nice solution to actually calculate the error. So what we're going to do to start is divide both sides by t minus a to the n plus 1. And the reason we're doing this will be clear later. So this is going to equal the n plus 1th derivative at a over n plus 1 factorial with a bunch of extra smaller terms with that value divided out. So all we've done so far is just cancel this value out. Now the reason we did this is to apply something called Cauchy's mean value theorem. So what this is, and it's very similar to the regular mean value theorem learned in calculus class, it's actually sometimes called the extended mean value theorem because it's just a more general form. What it states is that for some functions, f of x and g of x, where they're continuous and differentiable over the interval a to b, the following is true. F of b minus f of a over g of b minus g of a equals f prime of some value c over g prime of that value c, where c can be found between b and a. Now this looks very similar to the original mean value theorem, and we can actually prove the mean value theorem from Cauchy's because it's a special case by looking at the function g of x equals x. If we apply that to this formula, we get f of b minus f of a over just b minus a, and that's going to equal f prime of c over 1. And this is the regular mean value theorem. So we can see how it's a special case of Cauchy's extended mean value theorem. Now the reason we're looking at this is because we want to apply Cauchy's mean value theorem to the functions r of t, which we'll just call f, and t minus a to the n plus 1, which we'll call g in this case. So let's see what we get when we apply it. We know that the two functions r of t and t minus a to the n plus 1 are both continuous and differentiable over the interval a to x, where x is the value we plugged into our Taylor polynomial for an approximation, and a is whatever it was centered around. Now, if we apply Cauchy's mean value theorem, we get, where this is our f and this is our g, we will get r of x minus r of a over x minus a to the n plus 1 minus a minus a to the n plus 1. And this equals r prime of c over c minus the derivative of c minus a to the n plus 1, which is going to be n plus 1 in the front by the power rule, and the exponent will just become n. So this is the thing we've obtained by using Cauchy's mean value theorem. Now we can immediately spot that a minus a to the n plus 1 is 0. However, we also know r of a is 0. The reason we know this, we can look back at how we defined the error function. We know r equals f of t minus pn of t. And we know by the construction of the Taylor polynomial how we created it. We know fa is by definition equal to pn of a. That's how the Taylor series was made. And I have a video outlining how Taylor series are made and what they mean, which I'll link in the description. Now, this implies that the error at a equals 0. And we can go further and say the derivatives f prime of a equals p prime of a. And this is true all the way to the nth derivative of f, which equals the nth derivative of p. This is all because how a Taylor series is constructed. So this implies that r of a is 0, r prime of a is 0, and so on all the way to the nth derivative of r is 0. And the reason we're looking at this is because we're going to apply Cauchy's mean value theorem again to the results above. So first, let's rewrite what we have so far by plugging in these 0 terms. So we get r of x on the top over x minus a to the n plus 1 equals r prime of c over n plus 1 times c minus a to the n. And now, with these new functions we have, we can apply Cauchy's mean value theorem again. And we're actually going to repeatedly do this a total of n plus 1 times. So we will apply the CMVT n plus 1 times, which is going to give us a result for this initial formula where we can solve for r of x. So if we apply it to these new functions, f and g, we will get r double prime of c, of c. This is just kind of skipping a few steps, but if we want to see where this comes from actually, we can say that r prime of x minus r prime of a over n plus 1 times x minus a to the n minus n plus 1 times a minus a to the n, which is 0 again, equals r double prime of some other c over n plus 1 times n times c minus a to the n minus 1. This is by power rule again. And then, of course, we're going to do it again on these two functions. And if we keep going n times, we get this final result that looks like this. r to the n plus 1 of c over n plus 1 factorial. Because this exponent in the bottom term is just going to continually come down until our c minus a term cancels. So this is what we have, and we know it equals this original function by Cauchy's mean value theorem. So we know it equals r of x over x minus a to the n plus 1. So now we can solve for r of x, and we're pretty close to our final answer. So we get r of x equals the n plus 1th derivative of r at c over n plus 1 factorial times x minus a to the n plus 1. Now there are only two issues with this final solution. First of all, we don't know what r, the n plus 1th derivative of r is. And we also don't know what c is. So first, what is the n plus 1th derivative of r? We know by the definition of r, the n plus 1th derivative is going to equal the n plus 1th derivative of f minus the n plus 1th derivative of the n-term polynomial. And we know, because we chose the polynomial to have n terms, the n plus 1th derivative will be 0, because all terms will cancel. So now we're left with this. The n plus 1th derivative of r is the same as the n plus 1th derivative of f. Now we can plug this in to get even closer to our final solution. We have r of x equals the n plus 1th derivative of f now, evaluated at c, over n plus 1 factorial times x minus a to the n plus 1. And our final question is, what is c? All we know is it's some value between x and a. So what we do here is, since we can't find this exact solution for r without having to somehow solve for c, we can bound the maximum possible error. So to find the maximum possible error, where r of x is less than or equal to is bounded by this formula, we can just take the maximum value that the n plus 1 derivative takes at some value c, and divide this by n plus 1 factorial, multiply by x minus a to the n plus 1. And this is our final solution for the Lagrange error bound, where this max term comes in because we don't know what c is. We just know it's between a and x. So if we find the maximum value of the n plus 1 derivative, where c is between a and x, we can get some sort of bound on what the error could have been. And this is a very useful formula in finding the accuracy for a Taylor polynomial approximation of n terms.